This lesson is going to go into more detail about how to do electron configurations for ions and how to do orbital notation. So the first thing is we're going to focus on these ions, and just a reminder that an ion is something that has gained or lost electrons and become charged. So this is going to be any atom that has either a positive or a negative charge on it. Before you can focus on the ion part of it though, you need to go ahead and write the electron configuration as if it was a neutral atom. So let's start with magnesium, which is right here. And we're going to go ahead and abbreviate this so we can go up to beryllium and then go all the way over to neon, way over here. And we're going to put neon in brackets. And then we can start with the element after neon. And the element after neon is sodium. And if you look to the left of sodium, you should see a 3. And then the hat on top of it is S. And to get to magnesium, we're going to count across 2. So this is the abbreviated electron configuration for magnesium. But then we're going to look at that charge, and you have to recognize that the +2 actually means that it lost 2 electrons. It's opposite of what you think. So we're going to remove 2 electrons, and remember these exponents right here are telling you the number of electrons. So we actually just have these 2 valence electrons, and so we're going to remove those. But once you remove an exponent, the 3 and the S are just describing a region of space. So if there's nothing in that region of space, then it just doesn't exist anymore. And so the whole point of this is that magnesium with a +2 charge is going to have a similar electron configuration as neon. It doesn't become neon because the protons have not changed, but the electrons will be similar. All right, let's do the next one. We're going to do chlorine this time, which is way over here. And like I said, we're going to ignore that negative first and just write it as if it was neutral. So we're going to put neon in brackets again, up 1 and over to the right. And then we're going to start with sodium, which is 3s2. That gets us to magnesium. And then keep going all the way across. We're at 3p. And then to stop at chlorine, we are at 5. And so this time for our charge, we have a -1 charge. So we're going to add an electron. And we can't fit any more electrons in the S because the most it can hold is 2. But we can put 1 more in the P because the most it can hold is 6. And right now it has 5. So we're just going to change this 5 to a 6. And I want you to notice that when you have S2 and P6, that makes an atom especially stable because 2 plus 6 is 8, and that is actually a magic number in chemistry, that atoms tend to be more stable when they have 8 valence electrons. So if you notice in your homework and the progress check that you get a whole lot of answers that have S2, P6, it probably means you're doing it correctly because that's what it is in nature. That's what they go towards. All right, if you think you got it, so you're zoning out, this next one's a little different, so stay with me. We're going to do nickel this time, which is right here. So first we're going to go up 1 and all the way over to argon in brackets. Then we're going to start with the element after argon, which is potassium, number 19, K. And that's 4s2. Be careful for the overlap, so we're going to go down to the 3d, and then count over to nickel should be 8. So this time we're removing an electron because it's positive, and it's tempting to say 3d7 as your final answer. But for the positive ones, you can't just take away from the last thing that you wrote. For negatives, you'll always put them at the very end of your configuration, but for positives, you have to look for the biggest coefficient. So we have 4 versus 3. 4 is a bigger coefficient, and you always take it away from the bigger coefficient first if you have a choice. So in this case, we're going to take away 1 electron from this and make it a 1 instead of taking it away from the 3d8. So just be careful with the positives and then scan your electron configuration and find the biggest coefficients and take it away from those first. One note, if you have a choice between S and P, so say you had 4S and 4P, you take it away from the P before the S, but otherwise you just follow the numbers. All right, and then this last one, we have oxygen, which is way up here, so we're going to put helium in brackets. Then we have 2s2 and 2p4. And this time we're adding electrons, so again, we can't put any more in the S, but we can put 2 more in the P to make that 6. Notice that 2 in the 6, that means you're probably doing it correctly. All right, so let's go ahead and do some orbital notation. And this is helpful if you already have the electron configurations written. So the first thing we're going to do for each of these is to write the electron configuration. And then I'll show you how to do the orbital notation. So the first one we're going to do is silicon, which is right here. So we're going to go up 1 and over to neon in brackets. Then we have 3s2, and then 3p2. So go ahead and make sure you have that written first. Then you're going to draw arrows to show these electrons. So in the electron configuration, all we do is say how many electrons we have, but we didn't use arrows. So now if you can write somewhere on your paper SPDF 1, 3, 5, 7, that will help you. Those are the number of orbitals for each of those sublevels. So S will always have 1 orbital, P always has 3, D has 5, F has 7, regardless of the coefficient that's in front of them. So for example, for the silicon, let's go ahead and do a different color. So we have S to begin with, so we're going to label this as 3S. And notice that S has a 1 under it in that blue circle, so we're always just going to draw one line for the S. And then we're going to fill up the line with the number of arrows that this exponent tells us. And there are several rules. One rule is that you cannot put more than 2 arrows in an orbital, so you can't put more than 2 arrows on a line. Another rule is that if you have 2 arrows in a line, they have to be going opposite direction. That's Pauli's exclusion principle. And then the last rule I'll get to in just a minute when we do that P. Let's go ahead and fill up this S first. We have 2 electrons to put there, and so we're going to do 2 arrows, 1 up and 1 down. Now we're going to do the 3P, and the reason I drew the 3 lines is because P always gets 3 lines because of that 3 right there, not because of the 3 in front of it. It's just a coincidence. And when we're filling up these lines, we only have 2 arrows to put in these lines because of this little 2 right here. And Hund's rule says that if you have a set of orbitals, you have to put 1 electron per orbital before you come back for seconds. So if you ever draw more than 1 line, if you're doing the P, D, and the F, make sure that you put 1 electron per orbital before you come back for seconds. All right, and that's what it looks like for silicon. And so this shows scientists that there are 2 unpaired electrons, and that means a lot to scientists. So I know for you, you're like, why are we doing this? But it is actually really important in the world of science because it tells how things are bonded together and how they react. All right, let's do arsenic, which is right here. So we're going to go up 1 and all the way over to argon. Then we're going to start with K, which is 4s2. Go down to the 3d10. And then back up to 4p, and when you count over to arsenic, it should be 3. So let's start with the 4s, and we have 2 electrons. Remember, if you have 2 in the same line, make sure they're opposite spin. And then I did 5 lines for the D. These are all the D because of that 5 way up here. And we have 10 electrons, so I always just do ups first because then I don't ever mess up Hund's rule. And then if you have more, come back for the downs. And then the last one, we're going to do 3 lines for the P. And we only have 3 electrons, so we're just going to do ups in each one of those. And that's what it looks like for arsenic. And then the last one is strontium, which is right here. We're going to go up 1 and all the way over to krypton in brackets. Then starting after krypton, we have 5s2. And that's it. So 1 line with an up and a down, and that's the orbital notation for strontium.